All right. So from the do now question that I gave you guys, it was an question from the 2022 exam. So what the students that are year 13s took last year. And this was just asking you to draw an energy change diagram. So you have the reaction proceeds and you have the energy in regards to looking at the reactants and the products. The first thing you need to look for is this delta H here because that tells you the enthalpy of that reaction. And you're looking to see if that number is positive or negative. Since that number is positive, that tells me that is an endothermic reaction. If it was a negative number, then that would be exothermic. So with an endothermic reaction, what that tells me is that the reactants are going to absorb energy from the environment, and the products now will have more energy stored into them. So when we're looking at this marking schedule here, you see that the reactants, they're absorbing that energy from the surroundings, and now we have our products that have more energy than the original chemicals that we were dealing with. So that's one thing you should have drawn and shown. So the achieved point here was if you were able to draw that diagram and showing that the products have more energy than the reactants. They were actually willing to give up to a merit point for just the diagram itself, and that is making sure that you have the labels. So labeling reactants, products, and then the difference between these two is your delta H. So really easy merit point, I would say. Cool. Okay. The second part of this question then was asking about referring to the change in enthalpy and attractive forces between the particles of Freon 11. Explain how this process is used to cool a refrigerator. So a real kind of thing that we use in day-to-day life. So what we are thinking about in this case is the fact that these molecules are going to be evaporating from a liquid to a gas. Any form of evaporation is going to be endothermic because we have to absorb heat energy to break bonds. And so that's what it's saying in this little paragraph here. The breaking of the attractive forces is endothermic, so energy is absorbed for this to occur. Now, where is this energy coming from? This energy is coming from heat. And so that's then allowing the fridge to have that cooling purpose. So causing the temperature of the fridge to decrease. So it's absorbing that heat energy, making the fridge colder. Cool. So for the achieved, 2 different ways you could have gotten that point. If you just identified that attractive forces need to be broken or that heat energy is absorbed, they would give you an achieved point on there, that justification. Which is general definitions for when we're talking about endothermic reactions. Endothermic reactions have to absorb heat. Can I help you? I think I left my clicker here, but I don't see it. Well, have a look around the room. I haven't seen anything. You're welcome to walk around the room and have a look. All right. In order to increase this mark to merit, we're looking for linkages. So we're looking for you to use the word because or therefore, because that's showing that you understand that in order to break the forces, it needs to have the heat source. So it's just basically tying these two ideas together from the achieved. Okay? And then lastly, for the excellence was a full explanation about the cooling effect. So basically, I'm surprised that this actually does go up to an excellence. It's quite generous that this is an excellence point. What I'm looking at for a full explanation, it's very similar to biology. You've tied it back to the question. So in this last bit here, they're tying it back to the fridge. The other thing that I would say makes this a more full answer and a level, an excellence, is that they're talking about that they recognize the heat energy is coming from the surrounding. If you just say, oh, it's absorbing heat, it's not as a full answer as it's absorbing heat from the surroundings. So those would be kind of the things I would be probably looking for in regards for the excellence. And also mentioning of the fridge. Cool. All right, don't worry about madly copying this down because I have linked it on my Google Classroom. All the questions we're going to be using today are linked there. And also I've linked to the NZQA website with all the answers. So It's all readily available for you guys. Cool. Questions, concerns, comments? Keep going. All right. So let's talk about then the plan for today. So plan for today is I'm going to be teaching you this material using practice questions, so that way you can see exactly how you're going to be assessed on the exam. What we're going to do is I'm going to do one as an example, and then I'm going to let you guys do two for practice. The ones that I have selected, I've purposely selected because they are a little bit, I don't know what's the right word to use. They're tricky. They're a little bit of a curveball question. Other years, they've had really nice standard questions, but every so often they add an extra layer to the question, and it throws a lot of students off, and I want you guys to be prepared to take that extra step when you see that sort of information. So the other two questions that I've selected that I want you guys to work on are going to do that. And don't worry, I will do some clarifications at the end to kind of show you how I broke that question down. So that'll be the plan for today. I don't think we're going to get to the Mahi choice today, but when it comes to recommended follow-up, I would say, oh, I didn't even look up the SciPad pages for you. I will look up the SciPad pages and put it in there. And if you're feeling confident, you can just do the collated questions. There's no real need to do the scaffolding stuff if you get the calculations from the beginning. All right, cool. Let's do some math. So let me pass out the example we're going to use as our teacher notes. This one is a more standard looking calculation. It's not one of the tricky trickster ones that they occasionally throw at you. So this one is kind of more along the lines of what you will typically see. And then you'll see some ones that have basically just done something. It's complicated and I don't good. Especially if it's not up in the market schedule. All right. That's our second one. Just trying to be more organized. I don't want my paper everywhere. Mess. Okay, cool. So this one is also from the 2022 exam, a different section of the exam, but it's still looking at the Freon 11, which is the component in fridges to help keep them cold. All right, so let's look at how this works. So if you guys remember yesterday, I was talking about how there are two main categories of questions that are going to be calculations. The first one is going to be on bond number calculations, which is really easy. You just count up the bonds, do a little bit of algebra, figure out the number. So that was the first one. The second set is going to be these ones here that I like to call the enthalpy calculations or the energy calculations. What you are doing is you can work one of two directions. Either you are going from here's something that I have, how much energy is released or absorbed, or they can ask you to do the same equation working in reverse. Here's how much energy that was absorbed or released. Tell me how much do we need for that reaction. So that's forward and backwards. I'm only going to do the forward today, and then on Friday I'll do the backwards. So it's not too overwhelming. All right. So let's grab some markers. Okay, Freon 11 was identified as contributing to the hole in the ozone layer. It was banned in 1987. In the upper atmosphere, Freon 11 causes the decomposition, aka the breaking down of ozone, which is oxygen 3. Science people. All right. Here's the overall reaction for the decomposition of ozone and to oxygen gas below. So we have this reaction here, and we also have, we have this equation over here. This equation is already balanced, so you don't have to worry about doing any balancing of equations. That's already provided for you. And they've given you the delta H, which is their enthalpy, and they've given you a value here. Again, I can see when I look at it, that's a negative number, so that's exothermic. Now, what they want us to do is to calculate the amount of energy released. So we're calculating the energy released when you have 126 grams of ozone. Whenever I am looking at questions like this that require mathematical calculations and it's word-based, I like to annotate the question. Really useful if you're taking physics to do this. So this here is talking about mass. So I'm going to write that little m there so I remember that that's the mass. And then is decomposed into oxygen gas, and then they've given me the molecular mass of ozone. Are we good so far? All right. So my first step when I'm looking at this is I need to convert. So step one, we need to convert grams to moles. And that's a common thing that we do in chemistry because for us, moles is a far more useful unit because we want to think about it as an amount of particles instead of weight of the particles. So that's the first thing I need to do. So that then goes back to that equation, N equals little m over big M. You don't have to worry about having that memorized. They will give you that on the exam. So if I was going to plug in my numbers, I have 126 grams divided by my molecular mass, which is 48 grams per mole. I personally like to write down all my units. I suggest you do that for physics as well, because it's a nice little way to double check you've done things correctly. Grams and grams cancels, and I have per mole. So that tells me I'm going to get moles as my final unit at the end. So I've made sure it's set up correctly. So 126 divided by 48, and I get 2.625 moles. I'm not going to round at this point. I am not required to do so until my final answer. Happy? All right. Second step is I need to check my ratio. So when I look at this equation here, and I'm looking at the decomposition for the ozone, I notice for every 2 moles of O3 that decomposes, it is going to release 2,805 kilojoules. Now I want this value to be as 1 mole. So in order for me to do that, I divide this by 2. You guys okay with how I got the number 2? Got it from the equation. So we're doing 285 divided by 2. And so this would be 142.5 kilojoules per mole. And that's going to be energy released. So that's what I found here. And then my last step is I'm going to take these 2 numbers that I have and multiply them together. So 2.625 moles times negative 142.5 kilojoules per mole. Should say step 3, multiply. So I do those 2. I like to write my units down to double check I'm doing things correctly. I see the mole and the mole cancels out, which is good because I do want my answer in kilojoules. So I take that number and I get 343.0625. And I can write that that's kilojoules released. Now, we can grab the marking schedule, but I do want to kind of point, because I want to double check how they broke down the points. Remember that we do want this answer in 3 significant figures. So if I was to do that, that'd be 1, 2, 3. So I'd write 374 kilojoules released as my final answer. And that should, in theory, be an excellence point, but we'll look at the marking schedule to double check. Any questions so far? It's pretty straightforward as a calculation, I think. Can I move it? Not yet? Can I move it now? Okay. Let's go back to that marking schedule we had. I believe this might have been question 2. There we go. There's the working that we see. Got the right answer. Now, for the achieved, you had one step of this process correct. Any step in there correct. So it doesn't necessarily need to be the first step. It's any step in this process you've shown that you can do correctly. It is really important then that you show your working. Because if you make a mistake and you just write down your final answer, there's no evidence to the examiner to know where that mistake occurred and if you had done at least one step correctly. Now, since this was a fairly easy and straightforward problem, this one only went up to the merit level. All right. There's nothing here under the merit that's specifying significant figures in units, so I'm guessing they probably wouldn't ping you down for that. But when it comes to the excellence level answer, they do want the 3 sig figs and the units. So just keep in mind, usually the difference between merit and excellence is that. Okay. So let's give you some practice problems to do. They are going to be a little bit more tricky than the one I have just done, but I'm hoping with the foundation of what I've explained and some logic with reading the question, you guys will get it. Yeah. All right. Unfortunately, for some reason, NZQA does not have like 5 of the exam marking schedules for some reason. So I've used the No-Brain 2 small one. There are 2 different ways you could have gone about answering this question. So when we're looking at that, let me scroll to the original. Come on. Okay. So when I did the example, here we go. That's not what I wanted you to do. I must have scanned them in order. Okay. Anyway, so this question here is an example of like some wonky stuff they like to do to add like an extra layer of complexity that isn't really necessary. And then on top of that, they don't usually seem to add that in as a distinguishing factor between merit and excellence, which also annoys me. Anyway, we are talking about the production of aluminium. There were 2 things in here that were kind of in there to trip you up. The first thing being that they said 65 kilograms. You had to recognize the fact that you needed to convert that into grams because molecular mass is in grams per mole. Basically, you needed to know that you were using that 6,500 number first. The other thing that was a little bit tricky about this question was that this is the production of aluminium per minute, and they want you to figure out what is required per hour. I don't want you guys getting thrown off by this random extra stuff. All that's basically telling you to do is that you need to multiply by 60 at some point in your calculation to convert it from a minute to an hour. So the answer here, there were 2 different ways that you could have done it. You could have multiplied it by 60 from the beginning, or you could have multiplied it by 60 at the very end. Either way, you still got the same number, which is 1.21, and I think that might be 10 to the power of 8, because I can't see it being 108 kilojoules. Oh yeah, there's the number there. So do keep in mind, we want the 3 significant figures. Unfortunately, we don't have, like I said, the breakdown of the achieved merit and excellence point because they don't have this marking schedule on NZQA right now, so we need to tell them to put it back up. My guess would be if you did 1 step correctly, that would be an achieved. The merit would be getting this number, and then the excellence would be making sure you have 3 sig figs and the units. That's usually how the points go. They might have had this question be merit instead being you forgot to multiply by 60 or you forgot to use the grams versus the kilograms. So that might have been the distinguishing kind of question. Questions, concerns, comments? Ready for the next one? No. What? Why is that the what? It's fine. It's the exact same steps that you guys were doing before. Take the mass, divide it by its molecular mass, figure out the moles. Take the energy, divide it by the number of whatever we're solving. So in this case, since we are doing this working for aluminium, I look for aluminium in my equation. And I look for the coefficient for that aluminium. That's 4. That's why I'm dividing it by 4. And then I just take those two answers and I multiply them together. And then the only thing that's different is you multiply by 60 since they were asking per hour. All right, you guys can now do that back page. That is the 2021 exam, and once again, I will go over it. If you guys want, you can skip question A. I figure that's a good kind of reminder of things. Question B is the one that's more crucial because I want you guys to, again, practice those calculations. Cool. Move it. Okay, so this last question that I gave you was up here. All right. I won't really talk about this component here because of the main focus was going to be the calculations. So this one, again, is another example of a question that unnecessarily adds extra levels of complexity that really weren't necessary, but they've done it. So again, you guys have seen that they've given you a value in kilograms, just like the one that I gave you guys before. So being really mindful of which number you're going to grab this number here. All right. If you wanted to try to convert this kilograms into grams, you can take this number and multiply it by 1,000 for when you're working with it. Now, this is the fuel that has been loaded into the rocket, but the rocket only combusts 75% of it. So it's really a reading comprehension question. Did you notice that 75%? Did you multiply by 0.75 to actually count for the fuel that was actually burnt, not the total fuel that was there? So there was that kind of component to it. Let's look at the marking schedule for this guy. So wherever you put it in your steps was fine. They decided to take the kilograms and multiply it by 0.75 to first figure out how much fuel is being used. So that's the 75%. You could have done that at the end later. It wasn't a huge deal. But at some point in your equation, or sorry, in your math, you should have multiplied by 0.75. Then they took that value and they divided it by the molecular mass of our fuel. They got this value for moles. They checked the value for the enthalpy, which is 15,800, and they divided by 2. The reason why they are dividing it by 2 is because when we look at this equation here, since we are doing all this mathematical calculation based off of kerosene, we want the kerosene molecule, and I see that there's a 2 in front, so that's why we're dividing it by 2. And then I'm multiplying it by the moles that I got in the previous step, and then this is my final answer for how much energy is being released. 3 significant figures is the other thing to keep in mind, and you can write it either long way or you can do it abbreviated like that. Either or would be accepted. Cool. All right. Again, achieve point is one step of the process correct. So any step of that working being correct. So it doesn't need to necessarily be the first step. It could be a second step. So do take a guess and do try the whole thing because you might be able to fluke at least something that works. Merit was the process correct, but with a minor error. The way I read that as is the minor error is using kilograms instead of grams or forgetting to multiply it by 75%. That would be my judgment of what they mean by minor error. I don't, let me see what that question says. So I would get around that problem. I don't think they're going to be too like stickler on it because it wasn't like calculate the delta H. If you want to cover your butt and not have to worry about the positive and negative, I would say energy released, energy produced, energy absorbed. So that way you don't have to worry about if the units match. Cool. And then the excellence point here was to calculate the energy with correct units. So again, it's usually not a huge step up to the excellence, but I can see in this case, because they've added an extra layer to the question with that reading comprehension, they were using that as a distinguishing point between merit and excellence. Just looking at the one that was above, keep in mind that that guy went up to the merit level. It was very similar to what we did as our do now question. Identify that this reaction is endothermic or exothermic. So in this case, where'd you go? Again, looking at the delta H, positive or negative number. It's a negative number, so that must be exothermic. So that was the achieved point. This, again, is what I'm referring to is take a guess. 50-50 chance of getting it right, even if you don't know what endothermic or exothermic means. The other one is the delta H correctly labeled on either diagram, so just recognizing that it's the difference between the reactants and products that is your enthalpy. Now, something that you see here that we haven't drawn previously is this little like hill. This is just referring to activation energy, and it's just saying the energy that's required for the reaction to occur. It's not going to be the end of the world if you don't draw that. The main thing they're looking for is reactants, products, and the difference between them. All right. Merit point for that first one is correctly linking the energy of the reactants and products to an exothermic reaction to the correct diagram. So just explaining what you see. It's cool. So saying, I know that it must be diagram A because I can see that energy is being released because the products have less energy than the reactants do. So they're no longer stored in the bonds. They have been exposed to the environment. Questions, concerns, comments? Alrighty. That's us then.